Hello, everybody, and welcome to our next event in the DV Club Europe, where we're going to be focused on AI and machine learning in verification. A quick thank you to our sponsors, Agnesis, Cadence, Breca, Synopsys, Testhold, my employer, and of course our partners, TechWorks. Next slide, please. Okay, so today we have 271 people registered remotely. Represents 39 countries with 139 companies. Next slide, please. Okay, so we have three speakers today. We have the first one, who is Hardik Reina from Agnesis Incorporated. Then we have Paula and Matthias from Cadence, and finally David Kell from Breca, who of course we know well. We'll be starting immediately, and we'll be finishing at 1 o'clock. Sorry. Okay. Our first speaker today is Hardik Reina from Agnesis Incorporated, where he is an ML engineer. He's going to be speaking about genetic algorithms for automated verification from VCD data. He specializes in large language models and reinforcement learning with a strong research focus on generative AI and neural machine translation. He has contributed to cutting-edge AI innovations at Agnesis Incorporated and authored multiple papers in the field. He's based in India. Over to you, Hardik. Thank you.
Thank you. So, very good day to everyone, and thank you for joining me today. I would like to start by thanking the organizers of TV Club 2024 for this incredible opportunity to speak at such a prestigious event. My name is Hardik Raina, a machine learning engineer at Agnesis. My work primarily focuses at Agnesis on practical applications of AI and ML for hardware verification and other tasks. My primary focus is anomaly detection, IP verification, and more. Today, I'll be discussing an innovative approach to automated verification in hardware design, primarily using genetic algorithms. By leveraging the actual data present in value change dump as the input data, we've developed a framework that processes signal patterns and uses genetic operators to optimize test vectors. This method not only identifies anomalies efficiently, but also reduces the manual effort typically associated with the verification. I'm excited to share how this can significantly enhance the verification throughput and reliability. To start with, let's briefly discuss the need for hardware verification. Verification essentially to ensure that the complex digital system operates as intended. But it is a challenging problem indeed. With traditional methods, it's a time consuming task to track down the interactions between hundreds and thousands of methods and signals. These methods often require manual analysis, which becomes infeasible as designs grow in complexity and scale. Thus, highlights the need that we need to introduce an automation in detecting causally related signals and identifying potential anomalies. So we simplify the verification team's workload and the throughput shoots through the roof. For that, we're going to be employing the concept of genetic algorithms. Now, just how do we go about that and why do we use genetic algorithms in the first place? Well, so traditional algorithms that we might establish earlier, say brute force approach often requires a large amount of computation power that quickly grows infeasible. Amount of signals available in a standard VCD data quickly goes to polynomial time as we are forced to compute over and over and over again. Then comes in the GAs, form of heuristic optimization that mimics evolution. GAs iteratively refine groupings and generations, learning over time to find meaningful and potent signal patterns. This adaptability makes them suitable for our goal of identifying complex causal relationships in the signals. We might not be able to account for every variable that might influence the evolution of a, say, real world species like Homo sapiens or humans, but we certainly can simulate millions of years of evolution and testing of interdependent signals in a controlled environment such as the VCD data. Therein lies the input data. value change dump, which plays a critical role here. These files log signal transitions over time, providing us with a detailed view of how signals change in response to each other. This data is essential for analyzing cause and effect because it allows us to observe which signals change together or in sequence, establishing a precedence or a coincidence between different events as the simulation progresses, thus allowing us to establish a relationship going forth which signals affect which. Can infer the relationship between the signals, setting the foundation of a GA framework. Without even being aware of the underlying logic, the hardware implementation, these signals and their outputs alone are able to inform us of that much that we can establish a credible and reliable method to compare the design in the books and on the chip. So then comes a brief overview of a framework. Just achieve what we discussed. We are going to be parsing the VCA data to prepare it for analysis. Then the GA initializes a population of potential signal groupings and evaluates each one based on numerous vectors. Like through genetic operators like crossover and mutation, the GA iteratively refines these groupings. Finally, we use the highest performing groups to identifying anomalies, flagging unexpected signal behaviors, and more. This process automates what would traditionally be a manual analysis, making it more simple and efficient, scalable as we go on. And again, we need to remember our goal: simplify the workload of the engineer. Definitely don't want to be examining every possible correlation when the AI can sift through and present us with exactly what we need to be looking over. Only certain groupings or signal transition that actually are relevant to our task. As discussed before, in the first step, we need to process the VCD files and create an initial set of signal groupings. Parsing the VCD data provides us with the signals and their transition timelines. We use this information to set up the initial hypothesis. Basically, our first guesses about which signals might be related, which signals might affect one another. This step is critical because it gives the GA a structured starting point for the optimization product. The starting point or the initial population, as we'll be calling it further, can easily be constructed from the specification files to essentially give the model a head start, so to say. Then again, by the sheer nature of GAs, the randomness of the architecture will let us converge to the ground truth soon enough. Whether we have this initial hint or the design so assessed by the hardware engineer or not. Once we have the initial groupings, we need to find a way to assess how meaningful they are. This is where the fitness function comes in. We calculate time-lagged cross relations and mutual information between the signals to gauge their relationships. High fitness scores indicate a strong causal link between signals, while low ones might indicate weak or even adverse relationships. So this then helps the GA to prioritize the groups that serve to isolate the underlying patterns the best. For relationship, this measurement is a key factor in identifying which signals truly influence one another. Then comes the magic of randomness and evolution, the very heart of our framework. To evolve our signal groupings, we apply genetic operators, namely crossover and mutation. Crossover combines elements of two high fitness groups to produce new groups, while mutation introduces small changes. Steps allow the GA to explore a much wider range of groupings to avoid getting stuck in the local optima, where only a subset of the problems of the possible groupings are explored. Over time, these results are optimized, groupings that reveal causal relationships are surfaced, essentially boiling up to the surface to propagate further, to cross over, to multiply, to progenate, to reproduce till we have the optimal answer in our hands. For those curious from our experimentation thus far, we have concluded that to construct these groupings, order crossover and partial mapped crossover technique commonly used in the genetic algorithm space is quite useful in this regard. After all, the cause must precede the effect. This iterative process is the core of the genetic algorithm's learning phase, or the mind of the framework. Each generation of groupings builds on the previous one, retaining high fitness groupings and gradually improving them. The genetic algorithm's conversions towards high fitness groupings means that over many iterations, it hones in on the most relevant signal relationships. This continuous refinement is what allows us to develop deeper causal connections in the data. Our primary selection for the selection phase is a method known as the SUS or the FSR, commonly known as the stochastic universal sampling. These are some very interesting selection methods that can go on to promote a diversity of possible solutions or possible groupings that might be relevant to us. A signal that might not affect another in by itself might, in conjunction with another, quite readily affect the other. Even it gives the even the least fit member of the population an opportunity to continue improving, continue adding to our data and helping us find the answer. Well, that's for the theory. The principles that we build our learning on. Now we just put the theory to practice. See just how and why these genetic algorithms are expected to perform much significantly better than the algorithms that exist today. Summarize the spirit of the genetic algorithms, this genetic algorithm based framework offers several advantages. Firstly, it significantly reduces the time needed for manual verification. Second, it enhances the accuracy by surfacing the most relevant signals that might otherwise go unnoticed. Finally, because the genetic algorithm can handle large and complex data set, this approach is highly scalable, making it ideal for modern hardware verification tasks. We just need to explore the way forward then, right? By systematically analyzing these signal patterns, our approach identifies the irregularities outside the expected norms, allowing us to preemptively address design flaws. Detecting unexpected interactions helps us to isolate and resolve the issues that could impact design reliability, streamlining thus the debugging process. Here, the genetic algorithm is analyzing the VCD data to reveal causal relationships between signals. This approach is purely data driven, leveraging simulation outputs only. Thus, it really is independent of the nature of the bus itself, nature of the data itself. It relies solely on the data provided to it by the simulation results. This makes this approach independent of the exact underlying hardware, and we can solely focus on the results. By focusing on data and automating the discovery of signal relationships, this method significantly minimizes the time intensive manual analysis, enhancing productivity and accuracy. GAs, by their very nature, are highly stochastic. Discussed earlier in the highlight of the framework being mutation and crossover, we propagate and encourage the diverse range of solutions to carry over to each generation. Approach is highly scalable. In most practical cases, you can expect a linear time complexity, even if the theoretical maximum might tend to be infinite. Now let's move on to an example of some real life proved data. As you might observe here, this particular VCD data and the waveform therein is generated using an AXI bus. This AXI bus has produced a VCD data for us based on the particular design. And despite being in the preliminary phases of development, this framework has demonstrated significant promise by uncovering relationships within the VCD data. These relationships align with the formal descriptions provided in the specification files, and their validity is straightforwardly verifiable by a verification engineer. Results presented emphasize only the highest fitness candidates, presenting the strongest of the causal relationships, quantified by a measure of signal interdependence. The best fit, as you might see here, is identifying the encapsulated information and relating the relationship between the two. This conclusion, as the AI has concluded from here, suggests that the right address handshake on the LHS should logically precede or coincide with the right data handshake, RHS. The verification engineer is thereby tasked with confirming this assertion against the specification file rather than manually scrutinizing the entire VCD waveform. In essence, the AI identifies what is happening, leaving it to the engineer to determine whether it aligns with the design intent. This approach, even in its infancy, was promising results, taking sub-second time to analyze over 250 signals and establish concrete relationships between them. Once again, and with that, I would like to thank you for your time and attention. It has been a privilege to share my work with you today. I hope this session provides valuable insights into leveraging genetic algorithms for automated hardware verification. I'm happy to address any questions and discuss any potential collaborations.
Thank you, Hardik. That was a very good talk, and enjoyed that. And yeah, we obviously that's why we're doing that work on this, so we could collaborate as well. I actually used a genetic algorithm for the first time to do this type of work back in 1996, and I think there's did a paper online from myself and Jim Smith at the University in Bristol. It was good to see this methodology still being used. It's a very good, very powerful. So we have some online questions, which I'll read out. We've got a couple of minutes before we go to the next speaker. So they're asking exactly what is the fitness function here is the first question. Can you explain a little bit more about the types of fitness function you might be using?
So in this case, the fitness function is a common relationship between two signals. Say, a common causality relationship measure is known as the Granger causality. We've had to modify the existing Granger causality relationship for our own use. So the Granger causality, as it exists, it only exists for basically binary signals, say two signals that might move in tandem. The signals themselves being an analog signal, not the digital signal as we might expect in the industry. We've had to create a modified version of the Granger causality test that can handle multivariate data and that can handle a binary sequence instead of the usual analog signal that it might expect.
Okay, thank you. Our second question was on some examples, but I think you've given a good example there. So I will go to one of the other questions, and I think this will be our last one. How does this approach scale when the number of signals increases? What's the scalability of this, would you say, please?
Genetic algorithms, by their very nature, are really highly scalable. Mostly because genetic algorithms do not depend exactly on the size of the data, they more so depend on the fitness function. Herein, using the fitness function that we are using, being the Granger causality test, it's a simple mathematical test, basically performing a somewhat lengthy calculation to establish a relationship and get a final score that judges how fit a function is to be predicted by the other functions. What the best part about this is, it is really allowing us to allow the signals to basically spiral out of control. Even if they spiral out of control,
Okay.
the number of combinations we're exploring is very limited.
Okay, that's perfect. Okay, thanks, Hardik. There's a few more questions, but we'll send you those by email, and we'll get the answers to the audience. Okay, again, thank you very much, Hardik. That was an interesting talk to